And we have here today Zardosht Kasheff, did I say that I didn't pronounce that right, from Tokutek, who's going to talk about understanding indexes without needing to understand data structures.
So, hi everyone, I'm Zardosht. I'm probably going to keep my coat on. I'm kind of freezing right now. I work for Tokutek. We produce the TokuDB storage engine for MySQL. Yes, let's begin. So, understanding indexing without needing to understand data structures. So to start off, we're going to first start with some definitions. Let's define a dictionary as just a set of key-value pairs. We'll assume that you can update the dictionary, you can insert, you can delete, you can run updates, and that you can query the dictionary, and that you can do point queries where you select an element where, that's exactly equal to the key. And you could also do range queries. So for instance, I could find all the elements where a key is between two values. So B trees and fractal trees, I'm going to be referencing fractal trees a couple of times, it's the data structure used in TokuDB, are examples of dictionaries. Hashes, on the other hand, are not, because range queries are not supported. A table is just a set of dictionaries. So if, for example, we have a table that's defined with 3 columns, A int, B int, C int, and a primary key of A, and we insert a bunch of data, you can just conceptually think of the table as something like this, where you have every row, it's ordered by the primary key of A, you see this is the ordering, and with the key you have the entire row listed. The sort order of a dictionary is defined by the key. So for storage engines, you can just think about it as this, that range queries on a sort order are fast, and point queries for picking a particular value is slow. And in fact, a single point query is actually pretty fast, but if you need to read a bunch of rows this way by going and picking out individual point queries, that is very slow. An index on a table T is just another dictionary. So we need to define a key. We need to define the index as a bunch of key-value pairs. And the key of an index you can just think of as being the subset of fields that you define to be the index. And the value of the index, or the value in the dictionary, is just the primary key. There are other ways to define this, but for now we're just going to be sticking with this. So, for example, if you take the table we just had, and you alter it to add a key with the column B, you get something that sort of looks like this. You still have what we're going to call here the main dictionary, or the primary dictionary, that has all your data, and it's ordered by the primary key. And then you're going to have a secondary dictionary, or you can think of it as the index dictionary here, that is ordered on what you define, which is here B. And the value is going to be the primary key here, A, but you can just think of this value as just a row identifier. So if I'm looking at an index and I see something here, 56, 156, this 156 is going to be served as an identifier back into the primary dictionary right here for the entire row. So let's take a look at how just some queries would behave. I do select count star where A is less than 120. Well, this is just reading a range from the main dictionary that we have indexed here, and it gets the value. Another query, select count star where B is greater than 50. This also is another range query, which is fast. On the secondary dictionary, just looks it up, and it gets the values there, and that occurs pretty fast. But if you have a query, select some C where B is greater than 50, the information for what rows where B is greater than 50 is located here in the index, but the value of C that you're going to be summing is not located in the index. So what ends up happening is something that is a bit of a slow operation. You get the row identifiers here, which is fast, but now for each individual row, you need to go and you need to pick out what the value of C is here. And these individual point queries that are occurring are pretty slow. And you go and you finally get the value. And so this is the model that we're going to be using to understand what the performance of doing queries on a table is going to be. So what are indexes good for? The reason we have index is that it's going to speed up a bunch of queries. That's why you bother even maintaining them. So when you're designing indexes, what you'd like to do is you'd like to pick the most important queries and set up indexes for those. There's a cost for maintaining the indexes, which we'll get to at the end. But what we're going to focus on right now is how we're going to be able to design the indexes around our queries. And to do so, we're going to have just 3 simple rules for designing the good indexes. And we're going to avoid the details of any of the data structures. We're not going to care about B trees or fractal trees, which, while fun to know, it's not going to be important for understanding the performance model. The only thing we care about is that range queries are fast and point queries are much slower. That's it. Before getting into any of these basic rules, the first rule we should know is that there's really no absolute rule. Indexing is kind of like a math problem where rules help, but each scenario is its own problem. They have exceptions and whatnot, and it requires problem-solving analysis. But that said, rules help a lot, and here are the 3 basic rules. First one, we retrieve less data. The less data you retrieve, the less bandwidth you use, the less processing, things go faster. Second one, avoid point queries. Not all data access is the same. Sequential access is much faster than random access, so try to stick with sequential access.
Sorry, point queries meaning like just a bunch of individual queries, or
you remember that query where the animation was slow? Select some c where b is greater than 50. To figure out the value of c, it had to do a point query into the main dictionary.
Okay.
And for each of those rows, it was picking it out.
Got it.
The third one, avoid sorting. Group by and order by queries do a bunch of post-retrieval work, and indexing can help get rid of this work. So the first rule, retrieve less data. Let's start with a sample table that we have here. And you notice we don't have any indexes defined. It just has 3 columns, A, B, and C. And a query that you care about that matches 1,000 rows of the table, select sum B from foo where B is equal to 10 and A is less than 150. The query plan, if you don't have any indexes, is, well, it's going to scan the entire table. It's going to scan all, did I say so? Yeah, I said as an example, yeah, here, that the table has 1 billion rows, so it's going to scan all 1 billion rows, and it's going to filter out just the 1,000 rows you care about. Well, this is very slow execution because you're reading 1 billion rows just to get information about the 1,000 rows you care about right there. So what do? Reduce it. So you want to design an index by focusing on the where clause. This defines what the query is interested in, and the other rows are not so interesting. So in this case, the where clause that we care about is this, where B is equal to 10 and A is less than 150. That's what we're going to focus on to figure out what index we can design to reduce the number of rows we are processing. Well, the first thing, there are 3 options that sort of pop out. The option 1 is you use a key, you just use a key of A. Another option is you use a key of B. Now, what's better between these options? Well, it depends on the selectivity. If there are fewer rows where A is less than 150, then key A is better. If there are fewer rows where B is equal to 10, then key B is better. Now, there's also a third option here, which I'm going to address later, where you sort of use both a key on A and a key of B, and you merge the results. I believe you sometimes look in MySQL, you look at like the explain statements, you might see something along the lines of like using index merge or something like that. So we're going to get to that later. But for now, let's just focus on, you have the options for A and B. Well, neither A nor B is optimal, because remember we said at the beginning, well, 1,000 rows exist where B is equal to 10 and A is less than 150. But if you suppose where you have 200,000 rows where A is less than 150 and 100,000 rows where B is equal to 10, well then these indexes are still retrieving too much data. it's a lot better than what we started out with. We started out with a table with no indexes and retrieving 1 billion rows, and we sort of got that down to the hundreds of thousands. But really, what you want is you want something that'll try to just zero in on these 1,000 rows. And to do that, what you should try to do is you should try to optimize over as many pieces of the where clause as possible. So what we need is a composite index. We have 2 options for a composite index, A, B, and B, A. Now, which one do we want to pick? And this actually gets to a key rule for making composite indexes. In this case, you want to make the key B, A because the clause on B is an equality clause, and on A, it's not an equality clause. So here's the key rule. When making a composite index, place equality checking columns first. B is equality, A is not. B, A for this query is always going to be better. And if we take a look at an example for what happens on this table, you see that the query narrows it. Whoops. I thought that animation would move to the right. Sorry.
Does that hold true for OR clauses as well as AND clauses?
It doesn't hold true for OR clauses because you need to know both. You need to know all the rows where A is equal to 150, or A is greater than 150, and you need to know all the rows where B is equal to 5. So you're doing a union of them. So it doesn't work for OR clauses, but for where you're doing an intersect, it works here. Now, what if you don't have an equality clause for the columns that you have? So suppose your where clause was something slightly different, where A is between 100 and 200, and instead of having an equality clause on B, you have something where B is greater than 100. You have your options of a key of A, a key of B, a key of A, B, or B, A. Here's another key rule, where as soon as a column on your composite index is not used for equality, the rest of the composite index no longer reduces the amount of data retrieved. Adding other columns may still be helpful, as we see, but for the purpose of just reducing the data retrieved, it's really not much better. There are corner cases where it helps, but in general we can think of it like this. And an example for why that happens is, suppose where you have a slightly different query here, where B is greater than or equal to 5, as opposed to just equal, and A is greater than 150, what ends up happening in the range is you have this row here of 6, 101, where basically B is still greater than 5, but the condition on A is no longer true, sneaks into the rows that you're processing, and your query becomes more inefficient. In practice, there can be a lot more rows like this one here that don't exactly fit your where clause. That's the slide that had 2 pieces, okay. Now another example with composite indexes. Here where B is equal to 5 and C is equal to 100. Well, based on what we've said so far, we know that a key of B, C would work just great, but what if you had a key of B, A, C? That key, unfortunately, is only going to be as good as a key of B because A is not used in the where clause. So having C in the index doesn't help. Having B, C, A would be a lot better. And an example here is you get these rows here that sort of sneak into your range query that you end up not caring about. So let's recap the rules needed for reducing the rows retrieved. You want to create composite indexes based on the where clause. You want to place equality comparison columns at the beginning. And you want to make the first non-equality column in the index be as selective as possible. Once the first column in a composite index is not used for equality, or it's not used in the where clause, the rest of the composite index does not help reduce the rows retrieved. Why can I not say retrieved? Retrieved. That doesn't mean they're not helpful. In fact, they can be very helpful, and we're going to get to that in Rule 2, where we want to avoid point queries. So suppose we have a table here. Once again, we're just going to bring back the example we had at the beginning. You have a table here. You have 3 columns, A, B, C, primary key of A and a key of B, and your query select some C where B is greater than 50. The query plan is to just use the key of B, but the retrieval cost for each row is high because a random point query is done. And you recall, each of these elements that it's retrieving one by one using the row identifier here is doing a point query, and that can be very, very slow. Now what if we didn't use the key of B, and instead you just did a scan of the primary table? Now here is something that is sort of, I think, surprising about this, using just a full table scan, is that the retrieval cost of each row in a full table scan is really cheap. It's a lot cheaper than using point queries. The problem with table scans, as exhibited earlier on, is that you're just retrieving way too many rows, and it just sort of flies in the face of the first rule. But in some cases, table scans can be really good. So if I did something here where I did select some C where B is greater than 50, but I used a table scan, I used just everything here while retrieving all those rows, that's going to be pretty fast. The problem is you're going to be filtering out these rows that you don't care about. In our earlier example, when you're doing a scan of a 1 billion row table to retrieve just 1,000 rows, that's horribly inefficient. But those 1 billion rows you retrieve, the cost per row is going to be really, really good. So what if instead we added another index, and you added a key of B, C? Since you're indexing on B, you're only retrieving the rows we need. That's satisfying the first rule. But now the index has the information about C, so you don't need to go to the main table. You have all the information you need in this key to be able to satisfy this entire query. And you get no point queries. Just drills on the row, gets the value. That's very fast. And that brings us to a covering index. An index is said to cover a query if the index has enough information to answer the query. So let's take a look at a couple of examples here. You have one query, select some C where B is less than 100, another select some D where B is less than 100. An index of B, C covers the first query, because the only columns referenced here are B and C. The key B, D covers the second query, and a query of B, C, D is a covering index for both. So how can one build a covering index? Well,
sorry, can you
no, go ahead. Yeah, sure.
one slide?
Mm-hmm.
But with the key BCD,
Yeah?
that wouldn't be the most efficient index for Q, or so the second one. It technically is covered by it, but
Yeah.
if B is a very big number or it's not very selective,
Well, the where
it's not B. Oh, sorry, B.
the where clause is not on C here.
Oh, I'm sorry. Yeah.
Exactly. So that's actually an interesting thing here, where you have a key here where all I care about is B and D. But because my where clause is still as efficient as possible, in practice, this key is going to behave really well for both of these queries. Like, this key is going to be just as good for this query as it is for that query.
Okay, so as long as what's on the where clause is the first.
Yes.
Okay.
So how do we build a covering index? Well, you add every field. The key is to add every field from the select. A mistake that I have seen happening a bunch of times is that you have a query such as this where you select C and D from foo where A is equal to 10 and B is equal to 100. The mistake people make is they basically just apply the very first rule that we had. They just focus on the where clause. They say, oh, my where clause is on A and B. That's the only index I need. I'm going to make an index on A and B. And while it reduces the number of rows retrieved, and so in practice it'll make your query run a bunch faster, the fact that it doesn't cover the query causes you to have point queries to retrieve the values of C and D, and it still slows your query down. The correct index to have to really make this query perform well is to have A, B, C, D. You still place A and B at the beginning to satisfy the first rule that we were talking about, because you want to be selective on this where clause, and then you throw in C and D there to make sure you avoid the expensive point queries. Now what if instead we had the primary key matching the where clause? So queries select some C where B is between 100 and 200, but instead of having a primary key of A, we throw an auto increment column in here, and you make a primary key of B, comma, auto increment. We're throwing the auto increment in there because primary keys need to be unique, and so throwing the auto increment ensures that the primary key is unique, even though B may not be unique. Now the query is doing a range query on the primary dictionary. Only one dictionary is being accessed, and it's being accessed in sequential order. This is fast. So a property that we have here is that the primary key is going, if you're using the primary key, it's going to be covering all queries. And if your sort order on the primary key is matching your where clause, then basically your problem's solved. Now, what if a primary key doesn't match the where clause? Ideally, we want to be able to declare secondary indexes that just carry all of the fields, but unfortunately storage engines don't allow you to do this. So our storage engine, the TokuDB storage engine, allows you to declare an index to be clustering. And what a clustering index does is it basically includes all the other fields in the index data structure so that every query on a clustering index is covering, just like the primary key. So let's take a look at clustering keys in action. Suppose you have these queries. Select some C where B is less than 10. Select some D where B is greater than 200. Select C and E, and where B is equal to 1,000. Well, if I wanted to make covering indexes for this query, well, I can make BC to cover this one. I can make BD to cover that one. I can make BCE to cover this one. Or if I want to cover all of them, I have to make one with BCDE. This requires a lot of analysis of queries because not only do you have to predict what you're going to be selecting on, you're going to have to predict what data you're going to be retrieving. It's not just enough to know that I'm selecting on B. I need to predict, all right, what information am I going to be interested in? And this can be a bit of a pain.
So are you saying that you do the clustering doesn't actually cover everything, or like because it tries to predict what it is? Because in the last slide you said it's everything, all the rest.
No, it covers everything. The point I'm trying to make here is that if you have to predict what you're going to be selecting on, this is going to require a lot more analysis of your queries to try to predict the set of indexes that you have such that you're ensuring all your indices are covering. You know, 1 week from now, someone might come to you and say, you know what, instead of, let's not say B, let's just say timestamp, because a lot of people have indexes on time. They say, I want to know all the users that visited my website in the month of January. I want to know how much money I made in the month of January. And then someone comes along and says, on second thought, I want to know the number of unique IP addresses that hit the web. Not users, but the number of IP addresses that came in the month of January. We're like, wow, I didn't know you ever cared about IP addresses. I don't have a covering index that will maintain that. But a clustering index just just puts all the other data in there, the way that a primary dictionary puts all the data in there.
Is it like logging queries and then creating the indexes after it senses that there's a need?
No, it just has all the data there. You can think of it as just another copy of all the data in a different sort order.
Okay.
That's another way to think of it. But the nice thing that clustering keys allows you to do is it just allows you to sort of go back to the first rule where all you need to do is you need to focus on the where clause. In this case, a clustering key of B covers all these queries. And the nice thing is I can just start, all right, let me look at, what I'm doing over here, create a clustering key of B, and I don't have to worry about point queries anymore. Now let's go back to a query plan that I was talking about in the first rule. You might remember we had this query, select some C from foo where B is equal to 10 and A is less than 150, and we had 200,000 rows where A is less than 150, and 100,000 rows where B is equal to 10, and 1,000 rows where are sort of both. And we said that, okay, there's another query plan where you use key of A and you use a key of B, and you merge the results. Well, let's take a look at what that query plan is actually doing. What it does is it scans the 200,000 rows in key of A, where A is less than 150 in sequential order. It scans the 100,000 rows in key B, where B is equal to 10, and what it does is it accumulates the row identifiers. In our example, the row identifiers were the primary keys. So it figures out what all the primary keys are that match this, and it figures out what all the primary keys are that matches that. Then it merges the two sets of primary keys that it has, and it comes up with the 1,000 row identifiers, or primary keys, that match the query. And then it goes and it does the point queries with the 1,000 row identifiers. So what the merge plan does is, as far as the amount of data that you're analyzing, it doesn't really reduce the amount of data that you're analyzing. It alters the cost of the data that you're analyzing, and then it makes a lot more of the data that you're analyzing be sequentially accessed, and much less of it being randomly accessed. In this case, you have 200,000 rows and 100,000 rows being sequentially accessed, but only 1,000 rows being randomly accessed. So that's the way it helps. It's better than it's still better than no indexes, but in some cases still, even doing these 1,000 point queries can still be expensive, and you can still do better than that. If you just had a clustering key on A, well, then I could just scan the key of A for my 200,000 rows where A is less than 150. Because my resulting rows will already have the information for B, I can just filter out the rows where B is equal to 10, and then I'm left with the remaining 1,000 rows. So what ended up happening is I ended up doing a sequential scan of 200,000 rows and no point queries. Now the rows that I'm sequentially accessing are going to be a little bigger because it's going to have an entire copy of the row as opposed to just the row identifier, but a clustering key on A will get rid of the point queries. But the best thing you can do with a clustering key is go back to what we had with rule 1, define an index of B comma A, where B is what we have for the equality clause, A is the next field that we're selecting on, make it clustering, and there you're just drilling down on the rows you care about, and you have no point queries.
It
Yeah?
seems like that is just kind of like you're now indexing your indexes.
What do you mean?
Like the clustering key, so a clustering key with just A would be
A and everything else.
You would create basically a map of it where every single field has basically a combined primary key, A, comma, whatever.
Yes.
A, comma, whatever, A, comma, whatever for the entire table.
Yes.
Right? So, cool.
Mm-hmm.
I can see where that would be very fast.
Yeah.
But then now you're saying with where BA, you're now indexing everything with A and then B as well?
No, this is just a composite index. So the way that we...
But
I understand your question. So
the argument before, though, why the covering index is a problem is because you have to kind of guess in the future what you're going to need.
Yeah.
But isn't that the same thing there? You're kind of guessing what you're going to need to get that really high optimization?
Well, I'm guessing, what's different here is that you're guessing what you need for the where clause, which at least in my experience in speaking with customers, has been a lot more predictable than guessing what you're going to be doing for the select clause. The thing that makes clustering keys hard to predict is you don't know what you're going to select from it. What we're saying here is, all right, make your key clustering so you don't need to predict what to select from it, then but you still need to try to predict what you're going to be, what your where clause, how you're going to be selecting from it. And that still comes in time. I mean, like, people, I mean, it can still also be a little unpredictable, of what your where clause is going to be. But that's I find that to be a lot easier of a problem than trying to predict where my where clause and my select fields.
Thanks.
Yeah. Did that make sense? Did I answer your question?
Yes.
Excellent. So to recap the second rule, avoid point queries. You want to make sure that your index covers the query, and by mentioning all the fields in the query, not just those in the where clause. And if you don't want to bother with that, or you have a wide range of things that you may be selecting on, use clustering indexes. It'll cover all your queries. It'll allow you to just focus on the where clause, and it speeds up more and unforeseen queries. And it also just makes database design, I find, to be simpler. Now on to rule 3, avoiding sorting. Simple selects basically require no post-processing. If I have a select here from foo where b is equal to 100, I just get the data and I return it to the user. But more complex queries do post-processing. If you have a group by or an order by, it requires sorting the data. Index selection can help avoid this sorting step. So let's take a look at a couple queries here. Select count C from foo. No where, we're just eliminating the where clause to try to simplify things a bit. Or select count C from foo, group by B, order by B. Well, the first query plan is pretty simple. While you're doing a table scan, just count the rows that have a value of C and you're done. The query plan for 2 is a little more involved. You need to scan the table and you need to write the data to a temporary file. You then need to sort the temp file data by B, and then you need to rescan the sorted data, counting the rows with C for each different value of B. What we're going to do is we're going to instead use an index of B comma C. If you have an index of B comma C, well, the first thing we're doing is we're making this a covering index. The query is only referencing C and B, so that's going to be fast. But by having a key of B comma C, by sorting on B within the index, you avoid the sort during query time, and this makes this query pretty fast. So the take home here is that if you use the index to basically be your sorting index for the group by or the order by, you can avoid the sorting during query time.
If you choose between, you got the
Yeah.
greater than or less than and the equality.
Yeah.
If you have to do a sort, does that take precedence over whether to use the equality first or the?
I think I'll address that in 3 slides, but so let's actually put it all together and look at some examples. So the first one, select count star from foo where C is equal to 5, group by B. In this case, what index should we use? C comma B. You first have C to limit the number of rows retrieved. It's an equality clause. It honors rule 1. Then you have the remaining rows sorted by B to avoid the sort, which use rule 3. And because you've already retrieved all the data you care about, it's a covering index, so you have no point queries. Yeah, another nice take-home is that when you have where clauses on equalities, that works out really nice on indexes. Just equality. It doesn't mean, I'm not saying that the column needs to be unique. You could have 1,000,000 rows where C is equal to 5. That's not what I'm saying. But when your where clause has an equality, that just makes things really nice. Like, that's what makes this possible. Another one, but just a little different now. Select sum D from foo where C is equal to 100, group by B. In this case, we have a key of C comma B comma D. Once again, rule 1, put C at the beginning to limit the number of rows you're retrieving. Then you have the remaining rows sorted by B, so you don't have to do the post-processing sort there. And then you make sure that the index covers the query by throwing in the column D to avoid the point queries. Now sometimes there is no clear answer, and this directly addresses the question you were just having. I have select count star from foo where C is less than 100 grouped by B. The possible indexes here are CB and BC. First off, notice that they're both covering indexes, so we don't need to worry about point queries and analyzing which index we should choose here. Well, what's the query plan for C comma B? Well, first we're going to filter the rows where C is less than 100, but you're still going to need to sort by the column B. You don't get what we had a couple of slides earlier where the resulting rows of B are going to be automatically sorted, so you can avoid that. The reason is because C here is not an equality check, the value of B's are scattered in clumps for different C values. So for instance, all the values of B where C is equal to 0 are going to be sorted. Where C is equal to 1 are going to be sorted, 2 are going to be sorted, 3 are going to be sorted. But all the values of B taken collectively for where C is equal to 0 and 1 and 2 and 3 and so on all the way to 99, that's not going to be sorted. And as a result, this query plan is going to require a sort on B after it's retrieved, after it's done the filtering. The other thing you could do is you could have a query plan of B comma C. Well, in this case, you've sorted by B, so rule 3 is covered, but you're going to be accessing a bunch of rows where C is greater than or equal to 100, so you're not really taking advantage. So you're not taking advantage of the first rule that we had. And in this case, about the answer of what is better, well, it's going to depend on your data set. And this sort of, gets to earlier what I was saying is that, there are really no hard set rules. Everything is sort of dependent on the problem that you have in front of you. If you have a lot of rows where C is greater than or equal to 100, and saving time by not retrieving these useless rows is going to help, then use C comma B. But if there aren't that many rows where C is greater than or equal to 100, and the time to execute the query is really being dominated by the sorting, then you ought to use B comma C. So the point is, rules of thumb help, but it's a way to help think about the queries, and it's not just a recipe that you can blindly follow. And so why don't we just load up on indexes? Why don't we just, index every column, every possible combination we can think of, so everything, all our queries work fast? Well, indexing has a cost. And in this, what I'm going to do is, as I said, I'm a developer for the TokuDB storage engine, and with a big value proposition for our storage engine, it makes maintaining indexes a lot cheaper. And we're going to go into here what some of the costs are and how TokuDB alleviates some of these costs. Well, the first cost I bet that everyone points out, especially when they see clustering keys, is space. Each index that you're adding is adding storage requirements and adds up space in the hard drive. Well, compress the data. TokuDB, our storage engine, has aggressive compression, and we've seen between a 5x and 15x compression on our data versus NODB. The second issue that you have is performance. B trees, while they're fast for certain indexing tasks, like if all your indexes fit in memory, if you have 32 or 64 gigabytes of memory and your entire table is 2 gigs or 4 gigs, you can index the hell out of that thing. That's not really going to be an issue. If your keys are sequential, if I'm indexing everything on a timestamp, as data comes in, all my indexes are on time. For B trees, that's not an issue. But for other types of indexing, you'll notice as the size of your data gets really big, the insertion speed onto your table gets really slow. And what fractal tree indexes do, which is the data structure underlying for TokuDB, is it's fast at all kinds of indexing. And it can be up to 20 times faster than what you'll see with a B tree. The benefit is you don't need to worry about what type of index you're creating. So you can index early, you can index often. Another issue that users see is range query performance, and that the whole point that I was drilling down on rule number 2 is point queries slow, range queries are fast, and you want to use range queries. Well, That holds as long as your B tree doesn't get fragmented. I guess people are familiar with having to run optimized table to get their query performance, back up to snuff. What's happening is that your tree's getting fragmented there from deletions, from random insertions, and your range queries get slower. A benefit for TokuDB is TokuDB fractal trees don't fragment, so you never have to run optimized table for that. So for more information, you can feel free to contact me. My email is listed there at zardosht@tokutek.com for any thoughts, any feedback. I'd love to hear, what was good about the presentation, what, could use some more elaboration. I'm also going to be presenting this information on indexing in April at both the Collaborate conference in Florida and at the O'Reilly conference. And our website, tokutek.com, please visit it for a copy of this presentation. That's the tiny URL for it. And to learn more about the power of indexing and about fractal tree indexes and why it doesn't have the issues that you normally see with indexing that I sort of pointed out over the last couple of slides. We have some good information there. Or you want to see it in action, to download a free evaluation copy of our storage engines. And that's it. So I guess I'd open the floor for any questions.
Yeah, question about the clustering indexes.
Yeah?
So basically the clustering index covers all columns in the table, right?
Yes.
But you had an example where you were doing clustering index on B.
Mhm.
So that basically means B would be the first column, explicitly
Yes.
the first column covered, and then you did BA,
Mhm.
you were explicitly saying the first two columns covered. But I figure since all columns are in the index, even though you're only explicitly saying the first one in the clustering index on B,
Yeah.
there's going to be some implicit ordering that you could benefit for.
That's not quite how it works, and so let me actually use this right here. So suppose you have like a table of, I'm not going to bother declaring things integers and stuff, I'm just going to give the name. So you have a table A, B, C, D, E, all the way to Z. That's your table, you got 26 columns. And if I have a primary key of A, the underlying data structure here is you have a key value store where you have your key and a value, and the key here is going to be A, and your value is going to be the columns B, C, D, all the way to Z. For a clustering key of X. So this is for basically a PK of A, is what it looks like, where everything, the sorts are done just on A. For a clustering key of, I don't know, let's just say B, C, D. What ends up happening is your key is going to be, actually we make it B, C, D, and you know what, I'm just going to throw A in here as well, because, just to put the unique identifier at the end. And then your value is going to be what comes after D in the alphabet. E, F, all the way to Z. So really, the ordering benefits that you were talking about, you're still only getting it on the columns that you define. You also get it implicitly on just the primary key, but we're not, sorting based on the rest of the columns. That's just the value that goes in. Does that make sense?
Yep. Yeah, I can see the distinction there. So, but the size of the index is going to be the same either way, whether you're clustering on one column or more than one.
The size of the combined size of the key and the value for every row in the clustering index is going to be the same as the size of the key and value that you have in your primary dictionary. It's just that the order of things are shuffled around.
Yeah. And is the compression the same for the keys as it is for the value?
Is the compression the same? Well, that sort of depends on the distribution of rows. I mean, there could be times where, it might be that, like, if every key in your primary key, like, all the values of D are, all zeros. And then they're all ones and one, because they just happen to correlate with the primary key.
Right.
Whereas for the clustering key, that correlation may not be there. So I'd say that the compression's still really good, but how well you compress is based on your data distribution and how your data distribution correlates with with the order of your key.
Yeah. Okay.
Does that make sense?
Yep.
Okay. Yeah.
Question one.
Okay.
If you have a covering query on a sorting or grouping column, that's part of that. Is MySQL smart enough that for users that aren't aware of indexes and how to know there's an index or not an index and is writing their queries, and they tack on sorting and grouping, that it ignores that grouping and sorting because it knows it's already part of the index?
Yes. So I believe the question is MySQL smart enough to realize that the index has the sorting information and therefore it does not
really
need
doesn't
to
need
sort it into a temporary file? And the answer is, as far as I've seen, yes.
Yes,
Okay.
yes. However, I know that the optimizer, especially if you're using EnoDB, the optimizer has an estimate of things, and I have seen it choose an index that's in equality or range instead of the index that would help with sorting. Like the BC versus CB, that problem. I've seen it wildly do the wrong thing when it comes to that. Like it would choose to use the index that would sort the 1,000 rows that are left, but you'd have to go through like 10,000 rows to filter that out, and it wouldn't use the index to get those. You know what I mean? Like it would be better to get the 1,000 rows as opposed to having to look at 10,000 rows and then just sort the 1,000 rather than to filter without an index. I've seen it be vastly wrong on that in certain versions. It was a bug.
Okay.
I don't remember if it's fixed or not yet, but it was certainly something that was very, very, it was obviously one of those, this is wrong.
But if you have something that covers all of that and the sort, then that's not going to hit the problem. If you've indexed on all the different.
Well, if you've indexed on all of it, then the optimizer is going to choose one of them. And so if it has, whether it's a bug or it has inaccurate data based on what's better, because remember he said that when you have that certain scenario where you could use BC or CB, it's the size of the data and what you're getting that matters, right? If you're getting, if you need the filter to filter out, very little of it, then it's better to sort. If you need to filter out a lot of it, then it's better to use the sorting on filter. And so the optimizer can still make the wrong decision if it has bad metadata. But that has nothing to do with anything you can really control.
What kind of data is not good for B-tree? Obviously, sequential stuff's great for B-trees. Can you give just an example of like the kind of stuff that you might want to index that would be really bad for the traditional B-tree?
Well, the best thing that I've noticed in a lot of customer scenarios is really rule one in placing the equality clause at the beginning. So I want to know what user ID 5 did in the month of January. So what ends up happening, select star from table where user ID is equal to 5 and time is between January 1st, 2011 and February 1st, 2011. So the second piece of that query is not an equality. It's it's a range of date. But the first one, where user ID is equal to 1, is an equality clause. What ends up happening is people end up having a index of time, user ID, because that's the one that's fast. Whereas an index of user ID, time would be vastly superior. But because user ID can be basically random, users are just randomly visiting the site at all times, because user ID is random, B trees are going to have fairly slow insertion performance on an index of user ID, time, whereas for time, user ID, it's just going to chug along. So one of the things I've had to do when talking with customers, I say, okay, switch the order of that index, make it user ID, time, it will perform well with TokuDB. Did that answer your question? Or, I don't know, basically when it's random.
I could see if there's that randomness,
Yeah.
You don't. But,
Random insertion.
The way to get around it is you do it on the less optimal query using the date as your primary index, and then
And then you don't get as good query performance.
Yeah, as you could get by using something else. That,
So where B-tree indexes fall apart, generally I've noticed, is random insertions on random insertions, and the size of the index and the size of the table is so big that it does not fit into memory. So your table gets large.
when you're doing an insertion on B-trees or fractal, so if you have a single index, it's bounded by something, n log n or n log, whatever it is. Is it a constant, or is it a different factor when you start adding more keys to the index, or more things to the, so if you index on like 5 columns, is that just a constant of 5 fast, slower, or do you experience something to that log n?
How much, so the question is, how much slower is it by increasing the size of what you're inserting?
Of the key.
Of the key.
Because that might have
For
to,
fractal trees, the size of the key doesn't really matter. I mean, as the size of the amount of stuff that you're putting into the fractal tree, it matters. Where, you know, the more data you put, like, the more time it takes. It's not, you know, quite a linear. It's not like if I double the size of the row, it's going to be twice the slowdown. It's not quite like that, because as your row gets bigger, you end up just getting bound by writing the thing to disk. You actually get better, you know, write speed performance. For a B tree, I don't recall. I think the answer is, I don't know the answer well enough. I believe it does, where the size of the key as you increase it. I mean, it affects the number of pivots you can have in a node, but how well it affects it, I don't know off the top of my head.
Yes, there are some papers. It increases, the time increases. It's not linear, but it's, I wouldn't say it's quadratic or something, but it is not straight.
Is it for the same reason though, for the disk writing? I mean, taking away the disk writing. Is it just the tree structure itself? Because remember, MySQL doesn't, it balances the tree for you, the B tree.
Oh, that's
Give
good
or
to
take
know.
fragmentation.
Oh, that's good.
It is not linear, but it is not like quadratic either. It's less than that. I did some measurements up to 20 columns, and it goes.
Well, I know increasing the size of a key reduces the possible branching factor you can have in a B tree, and it has an adverse effect on the performance of a B tree, but it's sort of just one of those, you know, hard rules I know, and I don't quite, you know the details to know how to.
What about having a variable length key versus a
For fractal trees, it doesn't matter. I am not quite.
although
familiar.
I guess does MySQL? Yeah, I guess it does. If you have a varchar and you index the whole
Yeah.
thing, and it's, you know.
Sorry, are we talking about the length of the key or the number of imagine you have just like a very small bunch of columns and you make a key of like 20 different column field names, right? Is that slower than, say, a key that is a single key but it's bigger by itself than
Sorry, I was plugging it in. I didn't hear the beginning.
So imagine this, you got a column of tiny ints,
Yeah.
and you got 20 of them. Is that going to be faster or slower than an index with
20 bytes of
one
any other
column
information.
in a single humongous field
20?
of
20
twice
bytes.
as long or whatever?
Or the
That's
same.
just a CPU issue. That's not really. I
It's
mean,
not good. So is that how it does it though? It takes all of those fields and sticks them together and says, okay, that's your key, that one big string.
That's how TokuDB does it. I'm guessing.
That's how MySQL does. If you've ever had like a
Oh,
duplicate
okay.
key error or something, where you have a composite unique
Yeah.
or primary key,
Yeah.
it like says, you know, it has the thing like with a
Yeah.
dash in the middle or something. Or,
Yeah.
I'm envisioning in my head these more complex data structures where there's like a B tree and off this node is actually some other dimensional
No,
B
just
tree.
So I guess the good question is sort of just think of the actual key value pair that goes into that goes into one of these dictionaries, B trees, fractal trees, whatever, where the key is just the concatenation of the columns you define as the key, and the value, at least for the main dictionary, is a concatenation of all the other columns. Now, for variable length columns, you know, it just takes, the end result is variable length, but it's just a concatenation of the columns to create a key value store. And what ends up happening is there's a layer in the storage engine when it retrieves it that says, okay, I've got this blob, let me now pick it out and say, this is column A, this is B, this is C, and so on and so forth. So any question of like, do I have 2 4-byte columns or I have 1 8-byte column? That's just some C++ code somewhere finagling around with the 8 bytes. It doesn't really affect anything in the data structure.
I have a question about order of insertion. So if you insert new row with the keys and the new row does not violate the order of the indexes, does it mean that the indexes are not going to be reshuffled or recalculated?
If you're, are you for sequential?
Yeah, you have a sequential records and you index them.
I believe that if you are into a B tree, then it will not fragment. Like there's going to be balancing that happens as you're inserting. The tree is always going to be rebalancing, but the tree will not fragment, and you will not need to run optimized table. For fractal trees, it doesn't matter whether you're inserting serially or you're inserting randomly. Fractal trees do not fragment, so you do not need to worry about underneath the covers. Nodes need to get reshuffled for better performance. Does that answer your question? Okay.
So I had a previous job that I worked at had a underpowered MySQL database, and specifically the NODB database was running on a Windows machine, and we were having issues with having the disk subsystem keep up with the number of writes. We're getting about 8 updates a second to a table that had 400 million rows. And we were getting out of thread errors and system errors if we added too many indexes because we were writing too much data to the disk to a file that was also heavily fragmented. I mean, the NODB table file itself in the OS was getting fragmented. It had something like 4,000 fragments, and I tried to defrag it. You had to take the database offline to do it, and I never was able to convince anyone reasonable to do that. So how do you handle that? How do you handle a disk subsystem that's not always keeping up with the amount of I/O that you need? Because it sounds like you're storing data in the key.
We're not doing as much I/O as you think we're doing. I think that's the short answer, is that you don't have as much I/O for the writes that you expect. It's not and this is a whole other different topic of how fractal trees work, but a fractal tree does not incur a disk seek. It does not incur an I/O for each insertion.
Okay.
So the number of I/Os is just drastically reduced.
So what do you write into the fractal key to say, so when you go to retrieve it later, you know what's in it?
Is it in memory?
Huh?
Is it memory? It's got to write somewhere, right?
See, Barry wouldn't answer this question either. He was tap dancing on it when I started plugging him for.
That's not really fair.
That's fine, and he screamed NDA, which is why I'm here
No, it's
asking
not
you
NDA.
instead.
It's not NDA at all. It's question is, how do I explain it? Like, where's Bradley when you need him? So the question is, how is it that you can? What ends up happening is that it's like the data is sort of written in different parts sequentially, and then on a query, what you care about is sort of merged together, if that makes sense.
The queries weren't the problem. I mean, the queries were slow enough, and they would have. And as it turns out, I was able to replicate the entire database on another machine.
Are you talking about with TokuDB or?
No, this is on a NODB.
No, I was talking about what fractal trees do. Is the question what we said, that we do not do an I/O per insertion.
Well, I'm not so much worried about the read. I'm worried about the write.
Yes, on write we don't do an it's not an I/O per insertion, and that's what's different about. So what ends up happening?
Right, you're asking how to avoid it with ENODB, and he's saying use TokuDB. It doesn't do that.
So,
I'm sorry.
How does TokuDB reduce the amount of data that you're writing on the
We're not
file?
reducing the amount of data that we're writing in a file. We're just not writing it in a random order, so that you have to do a write. This is how it be.
So
Like
you're
basically,
coalescing it, but you're not. You're trying to.
I'm not trying to tap
together
dance, but like the things what I'm trying to do is I'm trying to avoid diving into.
It's more like
An
my
hour
ISO
to
where it's
write.
sequential write.
Yeah, I'm trying
So
to
you
avoid
don't
diving into a
spin
technical
disk.
talk that I'm not the expert on. but I understand well enough to be able to work for the company, but to be able to present it, it's like different. But I'll try to answer. So please go ahead.
Well, okay, so the other part is if you coalesce the writes, so you don't
Mhm.
write, you're still writing as much data, but you're trying to write it in clumps instead of
Yeah.
randomly. How does the recovery work?
How does
If the problem that we were having with InnoDB is that the MySQL server would crash because it ran out of OS threads to write data to the disk. And it would die with like OS error 9 or something like that. It was one of those nasty, fatal MySQL crashes. And let's suppose that you just, that
So how does recovery work after a crash?
yeah, because
Well,
that's how we found out we had too many indexes, is that the MySQL, we could watch in the Windows perf mon, it just started racking up threads and it couldn't write out all the data that it was getting fast enough to
well, the
keep
way
up.
that recovery works, I mean, the tree is checkpointed every so often, where it just writes the dirty information out to disk, and then we just log the modifications that happen to the tree. We don't necessarily log it, in a way. We don't log it in a way that's like make it look like a B tree. It looks like a fractal tree, but you log individual modifications that happen into the tree. You say, okay, I just inserted this value into the tree. I just deleted that value into the tree. And in the background, you checkpoint the entire data structure. So, I mean, does that make sense? So like the stuff that you've written to coalesce, that gets checkpointed like in a block together.
Well, this is a classic example of how much do you cache versus how much do you keep. When you say a commit, at the SQL level, and that's one of the things that we did, is we had a commit at the end of each insert because we were getting updates from multiple data sources.
Yeah, well, that's going to be slow regardless, but
yes.
yeah. Well, yeah, if you are committed, if you're syncing. Anyway, yeah. So go ahead, please.
So you would at least write to the journaling part of it
Yeah.
to disk at every commit,
Yeah, we do that.
and then
And
the extra index data that you have would also be written at that point too. So the
Doesn't
problem
have
was
to be,
is
but
the
yeah.
application was incredibly sensitive to how much data you were writing to disk because it was so close to running out.
If they are writing it to a log, like if
Yeah.
it's just this log that keeps getting written constantly, that probably can be fragmented to all high hell. And then they have it all in memory. The log probably goes for a while, and then it says, okay, now's the time to put all that stuff and where it actually is going to be in the right order. And then if it crashes in the middle before it does that, it has the log to.
Yeah, let's go back to the last checkpoint and do the recovery.
yeah, go back to the last checkpoint and replay the log. So
Yeah.
I guess I'm still not understanding the question
Um,
or the
Well,
mystery.
the issue was that there wasn't a lot of bandwidth. The write, especially the write in the disk subsystem on this box was really poor. I think it was just a badly configured RAID system, but I didn't think about that. Anyways, so it's sensitive to how much more data you're going to write to if you add more indexes. So, I mean, here you're talking about adding all these reasonably complex indexes, which is going to have more index data to
Yes.
write to disk, even if you write it in an intelligent and scheduled way. It's still more data sent to the disk that if the disk doesn't keep up,
Why would the disk not keep up?
because it was on a poorly configured host server.
I mean, I guess I'm not quite understanding.
It seems like the system you're using is on the brink of not working anyway, though.
Which is one of the reasons why I left.
Well,
Now,
I'm
that's
just-
before it crashed.
No, I know, but it seems it's kind of like, his might do more, but it was barely working to begin with.
Yeah.
So switching wouldn't necessarily fix it. It might write more, but
But
I guess you're kind of like my car's a junker and I put a better engine in it, but the rest of the car still sucks.
right.
Why is the car not running better?
Exactly.
It's like it still sucks.
Well, I think the essential question is, if you're switching from an InnoDB table with a lot of indexes
Yeah.
to a TokuDB table with a lot of clustering indexes, the values are the same size with InnoDB as they are with TokuDB. The keys are the same size, but the values are a lot bigger for TokuDB if they're
Yes.
clustering keys. So why is your insert performance going to be as good or better than InnoDB? given the fact that the values are a lot bigger.
The answer to that is that you're not going to switch from an ENODB table to a TokuDB table with the exact same number of indexes. The idea is that when you switch to TokuDB, you can have more indexes because the insert performance is better or whatever. You can actually index more than is feasible with ENODB. Because with
Right.
ENODB, you end up doing so much writing for the B tree index that it would end up taking so long for that write that it's not worth it to have that index, or it's difficult to have that index because now it's affecting production.
But why are the inserts faster on TokuDB if it's writing more data?
Because
the
it's
values
writing
are
more
bigger.
data, but it's writing it sequentially.
Okay.
So the disk doesn't necessarily need to spin as much to get to that right place or whatever, you know, or it's not looking at different places in the file to have to move around because the B tree is always balancing. So you
Yeah.
don't have that balancing like you do
Okay,
in the B
so
tree.
it's more data, but the writes are sequential instead of random.
Is that correct?
Very
Okay,
good.
great.
That explained it better than I could.
So in 5 years, when large solid state access is available, is the benefits of TokuDB going to be decreased because you're not going to have the latency on sequential writes that you have now?
No, because an inefficiency that you have with B trees is still that the amount of data you're writing per write is still very inefficient.
Right. When you're rebalancing, like if you put something into the middle of an index, let's say you have a dictionary, you put a new word into M, okay? You now have to rebalance the right half of that tree. So you're not just putting in one row, right? If you end up having to rebalance, you could have to rebalance O of N of the tree. You might have to rebalance the whole tree
Or just
at some point.
Yeah. Another way to think of it is, okay, I want to insert the word mom into the middle. What do I have to do? All right, for a B tree. All right, look up where this thing goes. Read in whatever it is, like 2 kilobytes, 4 kilobytes, 32 kilobytes. Read all that bunch of data in. Modify, boop, 10 bytes of it, and then eventually write it all out. So I just did a whole bunch of work for what was a diff of basically 10 bytes. And that's inefficient. And that's not using your bandwidth efficiently. So we actually have an experiment on our website somewhere where we have an insertion workload. And basically, it's a table with, it's called IIBench. It's a table with auto increment primary key, 3 secondary indices that are essentially random. The rows are generally pretty small. We ran TokuDB on a spinning disk, compared it to InnoDB running on an SSD, and TokuDB still outperformed by, I don't remember what, but like 10 something. You remember that experiment? Yeah, about like 10x. And the reason is the reason it still performed it had nothing to do with, you know, hard disks versus, you know, solid state drives, is that B trees are just inefficient with how they manage, with how much work they do for each I/O that they're doing. Whether the cost of that I/O is cheap on an SSD or it's really expensive on a spinning drive, they're not doing enough work per I/O the way that fractal trees are doing. So even on SSDs, fractal trees will perform really well.
8x.
Huh?
8
8x?
times.
Okay.
Order of magnitude was 10. So.
I just remember we had a curve. We were here, they were there.
It was very good.
We were here, they were there. Zeros are just not far, so that's what I remember. So, any other questions about fractal trees versus B trees? And like already, like one of the reasons, one of the things that sort of made us want to implement clustering keys was, we had like customers that they were like, they knew what their where clause was, they didn't know what their select fields were, and they were literally like throwing like a whole bunch of columns into the secondary index to make it covering. They made it so much that one of the very earliest patches that we did to MySQL, I don't know if you guys were here earlier, we were saying how in order to use our storage engine, we have a patch MySQL. One of the earliest patches we did that got adopted by MariaDB was we increased the number of columns that you can put in an index from 16 to 32, because we were finding like, oh wow, we want to get these customers to have, you know, covering indices. They need to start throwing in like 20, 25 columns into their index, and that was just becoming inefficient. I was like, you know what? We have compression. We're compressing by a good chunk. A clustering key is just not that much more expensive with TokuDB than just having a normal secondary key. So yeah, it's a little bit slower because you're putting more data, but for the query benefits you're getting, it's totally worth it.
Yeah, I don't really remember my data structure class that's going over fractal trees. I understand the B-tree. Can you, is there a quick and easy introduction of what a fractal tree is? Or is it?
No.
Can you put a link?
No, there isn't.
I can give a
I've-
shot, but I've got
I've
no
seen
guarantee.
Bradley's hour-long presentation, and I still don't
I'm not
understand.
Bradley, but I'm not
Alright,
Bradley,
so
so I
Can
I
you put a
can
link on the?
we'll
Yeah.
put a link. I can take a crack at it, but like, I
It's
mean,
kind of high level. Like you're very.
all right, here's a high. All right, I'll give this a shot, but if this fails miserably, can we turn the camera on? No, I'm kidding. Let's see. So
Let's see if I can actually get it on the chalkboard and see.
let's give
Chalkboard
this
I
a
should
shot.
turn the
So.
light on too.
So while I had data structures a while ago, a lot of data structures have been flushed from my head. So this is the way that I think of fractal trees. So forget about variable sized keys, forget about values, just you want to put data into a structure. And you have a structure that sort of looks like this, and just say everything is completely fixed up. You're just storing, just to make it easier, you're just storing integers, 4-byte integers, everything's just a number. So you have a data structure where you have a series level of nodes. At the very top, you have something that just holds one value. At the next level, you have something that holds 2 values. And the next level, you have something that holds 4. And the next, you have something that holds, 8. And let's see if I can still do this. What was that, 4? And so on and so forth. And the rule for inserting into this data structure is the following. Either at any given level, either that level is completely empty or it's completely full. So the very first thing I want to insert, let's just say I'm inserting in sequential order, I insert a 1. That goes there. And then I want to insert another value. Well, I take a look here, I was like, oh, well, it's full, so what I need to do is I get rid of that, and I do 1, 2. The next value I insert is a 3. And after that, when I insert, I go to insert here, I'm like, oh, that's already full, so I'm going to have to bring that, well, that's full, and it ends up being like, I already inserted 1, 2, 3, I'm inserting 4 now, right? So it's something like, then I insert a 5. It's kind of like binary counting on your hand if you've done this. Then I insert a 6, and it sort of becomes like this. Is it sort of making sense how data is getting inserted? Basically, you insert it wherever you can. You do whatever necessary merging you need to do, such that at any given level of the tree, it's either completely full or it's completely empty. So a way to think about what this data structure is doing is, well, first off, 7 out of 8 insertions, which is 87.5% of your insertions, is going to be happening up here. And this is always going to be in memory. So 87.5% of the time, you can just think, and this is like, how many bytes is this storing? Like, what's 7 times 4? That's like 28 bytes. Just for 8 values worth, nearly 90% of the time, that's going to be entirely in memory. Now, obviously, not everything can be in memory as this table grows. You're going to have, something here. This can be theoretically, megabytes, gigabytes long or whatever. That's going to be on disk. Now, what data in this data structure are you actually, forget, the asymptotics and, what big O notation, just what data are you going to be writing on disk? You're never writing these really small things up here on disk, because that's always just going to reside in memory. The stuff that you're actually going to be writing to disk are going to be one of these huge, giant blocks down here, which, the ones that are megabytes, hundreds of megabytes, gigabytes big. And the cost of writing that to disk, because it's such a big chunk, is basically going to be disk bandwidth. So in this data, now this obviously isn't the data structure we use exactly, because, you can't have someone do an insertion and all of a sudden a 4 gigabyte write happens in the background because, well, that was the one that just caused a merge in the 4 gigabyte level. Like, that's not going to work. But you can see in this type of data structure, for just the pure insertions, you're basically going to be bound by disk bandwidth, because anytime you write to disk, you're writing such a large chunk from somewhere here that it's going to go fast. So this is an example of a fractal tree where the insertions can basically run at disk bandwidth. What the big O notation and stuff is, I don't remember. I'm sure, you know, I'm sure like I can figure it out if I looked it up somewhere, but it's not important.
The insertion makes sense. What's the benefit of a lookup? Because like on a tree, you oh, go this way. Oh, go this way. How's a lookup done against something like this?
So basically what you need to do on a lookup for this is you sort of find the path down that you care about, and then that is going to be, I believe, something like log. So actually the lookup in this is not, I remember the asymptotic wise, the lookup of this is not perfect, or is not, you know, optimal. But what needs to happen is you do, you basically find the path that you care about. That's going to be basically log n pieces. And then you need to merge the results to figure out what the next one is. So I have something like log n values, and then I need to find the min of the value to see what the next element is. Then after that, the min of that. So actually, in this structure, queries don't work terribly well. But to come up with a fractal tree, but you can see like how queries are close to good. Now, what we actually do for, you know, how to make queries good in a fractal tree, that is hard to explain, which I can't quite do that. But at least from an insertion standpoint, at least, do people buy the fact that it's possible to have something other than a B tree that, you know, would be good? Like for a B tree, the really bad thing is, you know, you have something like, you know, nothing but pivots here, and you know, it sort of comes down and you have this, and if I want to insert something down here, in the fractal tree, 90% of the time, boom, it's coming up here. For a B tree that's really big, like all the time, or you know, if it's sufficiently big enough, all the time, like, all right, what block is it? Go to disk, find it, put it right there. The next one, go to disk, find it right there. Go to disk, find it right there. And that's incredibly slow. That's doing a disk seek every time. And that is hopefully the layman's reason for why fractal trees can achieve a lot better performance on insertions than B trees. So is this making sense? Because I've sort of only explained this on a one-on-one basis to people, never to groups. I don't know how well it sort of goes over.
So if you insert relatively large chunks with a fractal tree, they are not going to perform as well as if you insert the smaller chunks.
It ought to all work as, I mean, what do you mean by chunks? The number of elements or how
No,
big?
no. Just for each record will be like 100K. And you insert one by one those records.
Well, as the size of the row gets really large, it doesn't really start to matter for a B tree or fractal tree. For a fractal tree, it'll be fine, like, because you end up being bound by the amount of data that you need to write. Like imagine for a B tree, that the amount of data you're writing is just like, you know, megabytes large. And all your leaf nodes are like megabytes big. Then it really doesn't matter that I'm doing these individual seeks to write the data. Because by the time I do the seek, I'm already writing like megabytes worth. And that more than makes up, that's basically sequential, that more than makes up for the cost of the seek. So so I think in summary, for large rows, everybody's good. B trees and fractal trees, everybody does well. For small rows, fractal trees have a big advantage over B trees. Anything else? All right, well, thanks a lot.
Great.